So I will tell you about some simple proof for the Bose-Einstein condensation for bosonic system. Okay, so our motivation comes from the experimental facts in 1999. Thus, the Bose-Einstein condensation was observed in the lab. So this is the phenomenon when you cool down the Bose gas to a very low temperature, something close to the 0 absolute degrees. Then you observe that many bosons occupy a common quantum state. So in the pictures here, then when the temperature become lower and lower, then the momenta of many particles becomes identical. And this leads to many nice macroscopic quantum effects. So for example, the superfluidities or the quantile hypothesis. So today then we focus on the mathematical side of the phenomenon. For the non-interacting gas, then about 100 years ago, then Bose-Einstein already proved that you can actually compute exactly the fraction between the particles in the condensate over the total number of particles. Then what you find is on the right side here. So here T is the temperature of the system, and the Tc is the critical temperature for the BEC. So you see that when T is much smaller than Tc, or even if you can put everything in the 0 temperature, then you should expect the full condensation. Right? So what I want to talk about today is about the rigorous derivation for the BEC for interacting systems. So, and for simplicity, then I will actually focus on the 0 temperature, namely for the ground state or some excited state, but in the low light in spectrum of the system. Okay. So here the mathematical framework. So let me quickly tell you about the foundation of quantum mechanics. So we have a system of n particles, and this is described by a wave function. So here any particles live in 3 dimensions. So we have a Hilbert space of 3n dimensions. Right? And the wave functions can normalize from the physical point of view. Then the B size and square tell us about the probability densities of the positions, and the Fourier square tell us about the probability density of the momenta. And here, because we're dealing with bosons, so I always assume that the wave functions are totally symmetric. Namely, if you interchange the position of 2 particles, then the wave function remains the same. Then we have the Hamiltonians, which is Seiringer operators on the symmetric space. And when you take the L2 inner products of the wave functions and the Hamiltonian and the wave functions, then you get the energies of the quantum state beside n. Right? And from Hamiltonian, then you can find all the relevant quantum states. For example, all of the stationary states should be the eigenfunctions of Hamiltonians. So you have the stationary Schrödinger equations. And if you start from some non-equilibrium states, then you can compute the Schrödinger evolution using the time-dependent equation here. Right? So from the first side, then this description looks very simple because you just had a linear equation at the end. But the main problem here is you have the equation, linear equation, but in very high dimension, and you have too many variables. So in practice, this is impossible to compute the solution of Schrödinger equation either mathematically or numerically. So for this purpose, it is important to use some effective equation, which usually non-linear, but have much fewer particles or fewer variables. And our task here is to justify this approximation. Right? And the relevant parameter here is the number of particles. So we'll typically tuck n convert to infinities and try to derive some convergence of the n-body wave functions from the Schrödinger equation. Okay. So this is the general features in many-body quantum mechanics. So next, let me come to the detailed description of the Bose gas. So I consider a system of n bosons in 3 dimensions described by the following Hamiltonians. So here we have the non-relativistic kinetic operator for any particles. We have some external potential called U, and we have the interaction potential, I write Vn. So here for simplicity, I assume that the external potential is non-negative, and this convert to infinity when S convert to infinity. So the external potential here serves to trap the system. So this is why I call this the trapping potential. And for the interaction potential, then I thin up some short range interactions. So this some non-negative functions with smooth with compact support, and I assume that this has the specific scaling like that. So Vn equal to n square Vns. So here really you should thin up n square like n3 divided for n. So n3 and Vns give you something like the delta function, right? And then you divide this for n. So this is the relevant length scale because basically you have n square over 2 pairs of the interaction, right? So if any interaction has the order 1 over n, then the interaction energy would be up order n, and then this proportional to the kinetics and external potential energies. Then we might have to obtain some non-trivial limits when n convert to infinity. Right? So under this assumption on the potentials, then the Hamiltonian Sn is bounded from below. And we can extend this to be a Seiringer operators on the Hilbert space by Friedrich methods. Here we are interested in the stationary solution, namely the eigenfunctions of these Hamiltonians. And in particular, the first eigenvalues we call the ground state energies. So this can be obtained by the variational principle. So you just take the lowest energy as possible. Okay, so we want to get a macroscopic description for the ground state energies, or more generally the low-lying eigenvalues here, and also the information for the corresponding eigenfunction. Okay, so for this, then we need to derive some approximate theory, and the relevant thing here is the Gross-Pitaevskii theory. So this is basically the mean field approximation when you restrict your attention to the uncorrelated states. Right? So here you put the n particles in the same quantum state described by a function u in L2 of R3, and when you compute the energy per particles of this state against the n-body Hamiltonians, and you also formally replace the interaction potential by the delta interactions, then you will obtain the Gross-Pitaevskii functional like this. Right? So you have so this describe the energy per particles. Here you have the kinetic energies, the external energy, and now the interaction just the nonlinear term u to the 4 with some positive coefficient p. Right. So under our condition on the external potential that u convert to infinity and infinities, you can easily see that the variational problem, namely the infimum of this nonlinear functional with the constraint on the mass, has a unique minimizer up to a phase. And we can even choose the phases that the minimizer is non-negative, and this solves the nonlinear Gross-Pitaevskii equation like this. So these are the qubit nonlinear Schrödinger equations. Right. And here we have some Euler-Lagrange constant or chemical potential mu naught because of the mass constraint here. Right. And you know, by some standard regularity theories, then the Gross-Pitaevskii minimizer U0 will be smooth if U is smooth enough. So actually, for most of the purpose, then we just need the S2 regularity for U0. So we don't need to assume too much on the external potential. Good. So here there are some subtle points on the Gross-Pitaevskii function. So as I told you before, with our scaling Vn equal to n square and Vns, then we can thin up this when n converge to infinities, look like a delta functions divided for n, and then we get some coupling constant b, right? So what b is here? So the normal wedge would be b equal to integral of v, right? So this is the total mass. So this mathematically is correct, but physically is wrong. So this wrong in the meanings that if we choose b like that, then the Gross-Pitaevskii theory will not describe correctly the leading order of the dilute Bose gas. So the reason here is because the interaction potential is really large in its range. Right? So this is something like n square when s belongs to the support of the functions. And this create a really strong correlations in short distance. Right? So to correctly describe the dilute gas, then we have to introduce a nonlinear correction to this constant. So the right choice is given by the following formula. Right? So B equal to infimum of 2 times gradient f square plus vf square, and we require us f convert to 1 at infinities. Right. So here be careful, f not vanish at infinities, but convert to a constant 1. And actually, this related to the zero scattering problem. So this is why I can be the scattering energies of the potential V. Right? Then if V is nice enough, I mean, decays fast enough. So in our case, we just had a compact support, for example. Then this infimum problem has a unique minimizer, F between 0 and 1, and this solves the zero scattering equation like that. And actually, you can prove that Fs exactly equal to 1 minus A over S when S outside of the support of V. Right? And okay, so this is not surprising because if S outside of the support of V, then V here equal to 0. So F actually a harmonic function on outside of the support of V. Right? So 1 and 1 over S just the basis, two basis solution for the Laplacian f equal to 0 outside the support. Okay, and this actually nice because this tells us one equivalent definition of the scattering energies, namely the number b here exactly equal to a pi 8, where a here is the coefficient appears there when I do the expansion of f when s converts to infinities. Right? So the number a here called the scattering length of the potential V. So here there's some quick remark on the scattering length. So if you thin off the potential V like a hard sphere of the bone, say 0, and then had the radius r, then the scattering length is exactly equal to r. So the hard sphere means V equal to plus infinities inside the bones and equal to 0 outside the bones. Namely, you are not allowed any particle to go in the bone. So it's called the hard sphere. So physically, then in the dilute limits, then any particle will be felt by one of the others as a hard sphere. And by this reason, then the scattering length would be the natural quantity to appear there. Right? And in case when V is smooth, then you can compute you can one mass F, then V next you see the scattering energy here is strictly smaller than the integral of V, right? So for this reason, then the integral of V here is not the correct one for the dilute gas. Right? And by the trivial scaling arguments, you can see that when Vn scale like n square and Vns, then the scattering length of Vn is exactly little a over n. So this actually explains why we choose this specific scaling. Okay, so this will be our choice of the coefficient B in the Gross-Pitaevskii theory. Good. So now I'm able to state the main results today. So we start with the n-body Hamiltonian Sn like that, right? And we want to mark the connection to the Gross-Pitaevskii functional given by this one. So here I already replace B by A pi 8, and I get a 4 pi A here with A, the scattering length of the interaction potential V. Right? So our theorem is as follows. So this one work with Napiórkowski, Julian Ricaud, and Triay. So we assume that the external potential U is non-negative, locally bounded, and convert to, sorry, so here convert to infinities, infinities, not zero, the trapping potential. The interaction potential is non-negative. This radially symmetric, compact supported, and smooth enough. So actually we just need the L3 smoothness. And importantly, we need that the scattering length A here should be small enough, but independent of n, the number of particles. Then there are two conclusions. First, we know that the eigenvalues of the Hamiltonian Sn should be close to n time of the Gross-Pitaevskii energies. Right? So the closeness here is quantified by some constant independent of n, the number of particles. So in particular, the gross state and all of the low line eigenvalues should be at a distance bit over 1 to this number. Okay. And moreover, we can prove that any eigenfunction for Sn with respect to these eigenvalues with the fixed case, then this exhibit the complete Bose-Einstein condensation. So this formulate is as follows. If we do the expectations of the wave functions, again, the sum of B I, so here B is the rank 1 projection on the Gross-Pitaevskii minimizer. So when I write that the BI here means that the projection here act on the ith variables. Right? So the left side here is exactly the number of particles inside the condensate mode U0. Right? So the conclusion here is the number of particles in the condensation is exactly equal to the total number of particles plus some error of the other one. Right? So the error here actually optimal. I will explain later. Right. Okay, so this the main results. If you have any question during the talk, then please don't hesitate to interrupt me. Okay, so here's some previous results. So the leading order of the gross state energies was first proved by Lieb, Seiringer and Yngvason about 2000. So they proved that the gross state energies is equal to n time of the Gross-Pitaevskii energies plus something suborder. So actually the conversion in the energy will not imply the conversion of the states, namely the BEC. So in some later work, then Lieb and Seiringer prove that you do have the BEC to the leading order and something smaller. And some years ago, then together with Rothery and Seiringer, and then we found some simplified proof for this fact, and also the leading order here. And there are also some related results for the time-dependent problems. So in this problem, then you assume that the initial states satisfy some complete BEC. So you had a full condensation in U0 at the time 0, then you can prove that when the time t become positive, then the Schrödinger evolution here also had the this BEC, right? And the condensate here satisfy the time-dependent Gross-Pitaevskii equation. Right? So this looks exactly like the equation we had before, except that now you have the time dependent on the left side. Right? So this was first proved by Ross, Slide, and Yao in 2 papers. So first they proved this fact when the potential is small. So some conditions similar to our assumption at the moment. And later they found another proof that they can remove the smallness on the potential. And there are many work later when people derive some quantitative estimate and similar proof. Okay, so I want to come to some specific case. So this is called the homogeneous gas. So in this case, you put all the particles in the torus. So this is the unit spots in 3 dimensions with periodic boundary conditions, and you don't put any external potential. Right? So in this case, then the system is translation invariant, and the Gross-Pitaevskii minimizer is just the constants. Right? So in this simpler case, then people know more. So actually, the next order already computed recently by Boccato, Brietzke, Sinatiembo, and Slide. So they prove that the gross state energies has the leading orders n time of the Gross-Pitaevskii energies. So in this case, 4 pi a, and then you get some quantities about the 1. So this comes from the Bogoliubov calculation that I will explain later. And this formula is related to another formula called the Lee-Huang-Yang formulas when you compute the gross state energy in the thermodynamic limits. Namely, now you put the particle in a pulse, but you allow the volume of the pulse convert to infinities in such a way that the number of particles divided for the volume is fixed. So we call this rho. So when n convert to infinities, then the energy per particles here can be effectively described by this formula. Yes.
What's A?
A here is the scattering length of the interactions.
Okay.
So probably this looks slightly different from the previous. So here I use another slightly different. Okay, sorry for that. Yeah, but this the scattering length of the interactions.
Yeah, that's from something like Y law, right?
No. There are no Y law here. There are no semi-classic here.
Okay.
So the A is so maybe I come back there. The definition is here. Right? So if you do the infimum here, then you obtain 8 pi of 8. So this you can take this like definition of 8. Right? Okay. Or you solve this scattering equation and you find A in the Coulomb potential.
Okay.
So this really something related to the two-body scattering process of the particles. Okay, so this Lee-Huang-Yang formulas is proved to be correct in the so-called dilute limits. So this is something similar to the limits we consider here, but in the thermodynamics energies, then this count like the rho and A3 convert to 0. So this is not easy to see why this is related to the dilute limits, but actually this means that the rho here, when you take the power 1/3, is actually much smaller than A to the power inverse size. Or putting differently, then the length of the interaction is much smaller than the average length of the particles. Right? So in this limits, then basically any particle will see very few particles around, and then this is why we call this dilute. So this result was proved for the leading order first by Dyson for the upper bound. So Dyson paper went very early, right, in the same years when Lee-Huang-Yang wrote their papers. But this took like 40 years later when Lieb and Yngvason found a lower bound for the leading term. So this is a deep result. And the second order is even more complicated. So the upper bound was proved by Yao and Yin about 10 years ago. And the final lower bound for the second orders was proved by Fournais and Solovej last year. Okay, so this just to say that in the homogeneous case, then many things has no. Now we are consider the more general case with the trapping potential, and normally in the inhomogeneous setting, then the analysis become more complicated. Okay, so just give you some feeling on how the state look like. Then let us come to the upper bounds. So let's thin up the ground state energies En, right? And we try to give some upper bound for the energy per particles. Then by the definition, so En is the infimum of the energies, right? So to get an upper bound, you just need to find some trial state. Right? And of course, the first candidate would be the uncorrelated state. So you put N particle in the same quantum state. But if you do that, then you obtain this functional, right? So this is just a straightforward calculation from the n-body Hamiltonians. And here n time after Vn like n3 and Vns, this convert to the delta function with the total mass V, right? So this is the mathematical expression. And then this actually not good enough because you know that integral of V here is strictly bigger than a pi 8, right? So namely, if we do the infimum here, then you will get something strictly bigger than the Gross-Pitaevskii energies. So this choice is not good enough even for the leading order. Right? So a better choice is the following. So we take the n-body wave function, like we put again the uncorrelated states, but you also create some correlation of the particles. Right? And the right structure of the correlation here is taken by just using the scattering solution Fn from the Vn. So actually by the trivial scaling, you can see that Fn is exactly equal to F and S, when F here is the scattering solution for V. Right. So this just scale like that. So right, and then if you just insert this ansatz and then compute the ground state energies, I mean the expectation of this one against the n-body wave function, again the n-body Hamiltonians, then up to some simple approximation, you can derive this upper bound. And now, now you see that you can already effectively replace the n time of Vn by another function g, and g here look like following. So g equal to n3 and gns, where g just 2 gradient f square plus vf square. And then you see from these quantities, this should convert to the delta function, but now you get integral of g, not the integral of v. And when you do integration here, then you obtain back the a pi 8. Right? So this is the right scattering length. Right? Okay, so all of those give you the leading order for the upper bound, but not yet with the right error estimate. So actually to get the beta bound here, we need a little bit more complicated trial state. And this will be constructed using Bogoliubov transformation on Fock space. But I will skip this part. So this slide just tell you that somehow we want to see some function with the full condensation, but also the correlation between particles become important. Right? So this is something we have to keep in mind. And in many places later, we have to consistently replace the integral of V by the right quantities a pi 8. Right? So integral of V here is just the leading order in the bond series expansion of the scattering length. Right? So then to get the full scattering length, we have to do something clever. Okay. Then now I want to discuss about the lower bound because this is more difficult. And for that, we need to use the language on Fock space. Right? So the reason here is because we want to understand the behavior of particle outside of the condensation. So here we have a total number n particles, but we don't know how many particles inside the condensate and how many outside the condensate. Right? So for this purpose, we don't want to fit the number of particles. So then we come to the Fock space, namely we take all possibilities of the number of particles. So the little n here can run from 0 to infinity, and we take the Dirac sum. So we get the Fock space. On the Fock space, you can define the creation and annihilation operators like that. Okay, so probably some of you are not familiar with this language, so let me go slowly here. So let's consider the B side is a little n wave body function. Right? Then the A star G will create the n+1 wave body wave function. Namely, you create one more particles, and the action here is as follows. So you put the B side here, you touch the n variables there, and then you put the missing variables by the function G. Right? And of course, you want to mark the resulting function here is totally symmetric. So I have to take the sum when the J here run from 1 to little n+1, and even I put some combinatory factor 1 over square root n+1. For the purpose we see later here. And for the annihilation operators, then you start from some n little n body wave functions, you q one particles, and you end up with wave function of little n-1 particles. Right? And for killing a particle, I mean, you will take the inner product of one variable there. Right? So here actually the B side is symmetric already. So when you do the inner product here, then the resulting function here is always symmetric in the first n-1 particles. Then I don't need to do the symmetrization, but still I have to put the prefactor square root n. Right? So this factor has included to ensure that we have the canonical commutation relation. So the CCR, namely the A and A, they commute, A star, they commute, but A and A star, the commutator here, this is non-zero, and this is given by the inner product of the relevant function. So here, this is the L2 inner product of G1 and G2. Okay, then for further calculation, we will take an autonomous basis of L2. So here it should be R3. And we can, of course, do the U0, so U0, the Gross-Pitaevskii minimizer. But for U1, U2, U3, we can take any guys to form some autonomous basis. And we denote by AN by the annihilation operators of UN for simplicity. Then the CCR here, you can rewrite like this form. So AM, AN, and AM star, AN star equal to 0, and AM, n star now equal to the delta function of m when m equal to n. So here should be inner product of um and un. Okay, so this is the formulation on second quantization, and this allows us to reformulate the problems. So the original n-body Hamiltonian can be extended to be an operator on Fock space given by this formula. So here we had a creation and annihilation operator, AM, AN, AM, AN, AB, AQ, with the coefficient little s and W. They are given by the following formula. For the one-body bus, you take the inner product of UM and UN with the kinetic operator and the external potential. And for the interaction, then you take the inner product, but in the two particle space. Right? Then you get the UN, and UP, UQ there. Right? So here, you had the exact equality, and this just independent of your choice of the basis UM. Okay, and now for the complete BEC can be reformulated as follows. So the left side here is the expectation of the particles inside the condensate, namely inside the U0 mode. And this is exactly equal to the expectation again the U0 star and U0. And for the complex BEC, we want to prove that this one is equal to n plus bit of 1. Right? And this just exactly equivalent to the fact that the total number of particles outside the condensate is of order 1. Right? So here n plus means the sum of an star n when n different from 0. And this is exactly equal to capital N here as a number minus for A0 star and A0. Right? So this is the number of particles outside of the condensation. Okay. And for the lower bounds on energies as well as the complex BECs, then we will derive both from the following lower bound. So we prove that the n-body Hamiltonian actually bounded from below by n time of the Gross-Pitaevskii energies and some positive constants coupled with n plus. So the number operator here and minus for some constant about the 1. So here C is a large constant but independent of n. Right? So this is our goal to get a lower bound. Good. And the ideas come from Bogoliubov theory. So in a famous paper in 1947, then Bogoliubov subjected the following formal approximation. Okay, so he subject that we start from the second quantized form of the Hamiltonians. Then you do 4 steps. The first step here is you ignore all term with 3 or 4 operators, an when n different from 0. So the idea here is because he expects the full condensation on the 0 mode, right? So this means that A0 somehow much bigger than the other an with n different from 0. So if you think about the perturbation theory, then the term with more than 2 creation or annihilation operators, an with n different from 0, this should be much smaller than the other term. Then you just simply ignore those. Right? Then after that, you are left with a simplified Hamiltonian, and you can even make it simpler by replacing any A0 or A0 star by a C number. Right? So here I write this square root of n0. So this is called the C number substitution. Well, this sounds a bit crazy because you cannot replace an operator by a number, right? So the operator here even not reserve the number of particles, and here is something totally different. But the ideas behind is you can think of the n0 here like the expectation of the wave function again the A0 star and A0, namely the total number of particles inside the condensate, right? But remember that when you compute the expectation of A0 and A0 star, then you get number 1. Right? So this means that when you evaluate the the expectation against N0 star and A0, then you get something much bigger than the commutator. So you can think of A0 and A0 star, they almost commute. Right? And when they commute, then you can even think of they are just like a C number. So this is a little bit formal, but we can accept this at the moment. And after doing 2 steps there, then you obtain a quadratic Hamiltonian on Fock space. So quadratic meaning you get something with the 2 creation or annihilation operators in terms of an when n different from 0. And for these kind of the Hamiltonian, you can diagonalize explicitly using a simulated transformation. So something when you replace the AP by some transformation like that, so you will make up a new creation and annihilation operator A tilde would still satisfy the CCR. Right? So this is what we will normally call the Bogoliubov rotation. Okay, and the last step actually subjected by Landau when he read Bogoliubov writing. Then he realized that if you do all of the first 3 steps, then you will obtain some wrong formulas. So this is wrong because you will get the integral of v instead of the a pi a. So this is something similar when we saw before for the upper bound. Right? Then Landau suggested that anytime when you see the integral of v, just replace this by a pi 8, and then you will get the right answer. Okay, so this sounds strong, but if you believe on up the 4 steps, then you obtain the following approximation. So Sn close to n time of the Gross-Pitaevskii energies plus with the Bogoliubov energy, so something order 1, and you get a quantization of some positive operator. And now the BEC basically follow from the spectral graph, namely the infimum spectrum of the operator psi here. When you come to the orthogonal space of the condensation U0, then it's strictly positive. So this is the ideas of Bogoliubov, and somehow we try to regress his arguments. Okay. So the main message here is justification of Bogoliubov approximation is difficult. Right. So actually what I tell you today is we will not really come to the own step here, but we find some easy ways to somehow try to implement some parts of his ideas. And it's enough to derive the BEC for the dilute gas. So probably this simpler to start with the homogeneous case. So here we put particles in the torus, right? And without any external potential for simplicity. So the idea is as follows. So we just complete the square. Namely, we have the following inequality in the 2 particle space. Right? So this just trivial inequalities because Vn here is non-negative, and this operator just the H-on of the other one. Right? Then here we think of the Vn and Fn as the multiplication operators on 2 particle space, and P the projection on the condensate U0. So in the translation invariance, then U0 just the constant function 1 in the torus. Right? So if you insert this inequality there and you expand this, then you obtain the lower bound here for the Hamiltonian. Right? So this look complicated, but you just need to see that here you see the AB star and AB when be different from 0 just come in the quadratic term, right? So either you should have a 0 B when be different from 0 or 2 term AB when be different from 0, right? So there are no cubic or quadratic terms. I mean, there are no 3 or 4 terms with AB when be different from 0. So actually we already did the first step in Bogoliubov arguments, right? And here actually we also did the last step, namely the Landau correction, because we already replaced the potential Vn, interaction potential here, by Fn and Vn, right? So why this corresponds to the Landau corrections? Because now we can just do the integral of Fn and Vn, right? And by the definition of the scattering length, you see that we will get the right answer, not the integral of V anymore, right? So you see this. This is a simple but very useful trick, because just by completing the square, then we can immediately implement 2 important steps in Bogoliubov transformation. Right? So we get the ideas from a paper of Brietzke, Fournais and Solovej when they work on the Lee-Huang-Yang formulas. So they use slightly different form, but the ideas are similar. Okay. Now we are left with 2 other ingredients in Bogoliubov argument, namely the C number substitutions and the simplistic diagonalizations. And again, both of those can be implemented by a single inequality. So this we have this inequality. So for any operator P in the Fock space and any constant A and B real non-negative number, and then you do have the lower bound like that. And this actually comes from completing the square again. Namely, you can rewrite this inequality like D star D non-negative for some operator D. So this we took from the paper of Lieb and Solovej. And we can apply these inequalities for P equal to A naught star AP divided by square root of N. So here you can think of BP very close to AP if the A naught close to square root of N. But if not, then this just some clever way to do the C number substitution. Right? Then you can prove that the BB smaller BB star smaller than AP star, and the commutator here is smaller than 1. So this upper bound is good for our lower bound, because when we insert there, then you see that this is a negative number, right? Square root minus A. Then together with this one, then you get a lower bound. Okay, then we just insert there, and then we can prove that's the Hamiltonian with minus for the term with the 4A naught, and then even minus for mu of A n plus with some good number mu. Then you can bound this like the quadratic Hamiltonian in terms of the B like that. And then you can use this lower bound, you get the exact equality there. And you can evaluate this term here using the scattering equation. And you can compute the Fourier transform there, and you pass the sum to the integration, then you end up with this formula. Right. So this is something on the end. This not fully give you the Gross-Pitaevskii energies, but this will come soon. Okay, so then this is what we prove. We get mu of n plus, and then we get some contribution from the 4A0, and then this from the quadratic terms. Right now, finally, then I rewrite this term in terms of n plus. Right, so this is easy. Then I just insert there, and you see that the number here is exactly equal to the Gross-Pitaevskii energies. So here I get exactly 4π8. And then finally, I want to mark this constant positive. Namely, I want to choose mu, such that mu is smaller than 4 pi square minus A pi A because of another constraint there. And then I get the lower bound. So if A small, namely A smaller than pi over 6, then we can do that, and we obtain the desired lower bound. Okay, so this is the full proof in the homogeneous case. So this is really simple. We do nothing but basically complete in the square. Okay, so then for the general case, then this become more complicated. So I don't think I have enough time to explain, but maybe just one point that now you have the quadratic Hamiltonians, which is more complicated. So you cannot just compute the gross state energy of the Hamiltonian here by completing the square. You have to do something more general, and this here. So for the quadratic Hamiltonian, we can actually compute the leading order of the gross state energies, and this is given by some quite general expression using the abstract functional analysis, and then you can actually compute everything. So I will skip the detail here. Maybe I use the last 2 minutes for a remark. So we have that our derivation of the BEC with the optimal estimates will be useful to the following problem. So this the conjectures on the excitation spectrum. This contained explicitly in the paper of Bogoliubov, and the formulation I took below is taken from paper of Ricaud and Seiringer. So the conjecture here is follow. Consider this operators. Right? So here D is just a mean field operator from the Gross-Pitaevskii functional. Right? So you get this quantities you subtract for the chemical potential. So these are non-negative operators with the zeros, the first eigenvalues, and then you get the next one, and so on. And you end up with this operator because the complicated Bogoliubov transformations. But this operator has the compact resultant, and this has a sequence of eigenvalues convert to infinities. So the conjecture here is that the EI here give you the elementary excitation of the spectrum of the n-body Hamiltonians. Namely, any eigenvalues of Sn close to the gross state energies should be the finite sum in of EI. Right? So here you just put the EI. You can put any integers, a number and I here 0, 1, 2, and when n convert to infinities, then the sum here gives you all of the eigenvalues. Right? So this kind of result already proved in the mean field regimes when Vn replaced by n-1 V. So this is a much simpler regime because you don't need a Landau correction in Bogoliubov theory. This was first proved by Seiringer and Seiringer and extended by other people. And in the dilute limits, then this just proved recently by Bogato, Brennecke, Sinatiambo, and Slice. So in this case, then the excitation, elementary excitation given exactly by these quantities. And you see that when you take the infimum of EP over P, right, then you get something strictly positive. So this is actually a nice justification for the Landau criterions of superfluidities. Namely, if you put a drop in your condensate with a velocity less than this number, then the drop can move frictionlessly in the growth state, because you will not change the growth state if the velocity is not big enough to beat the linear behavior of the elementary excitation. Okay, so I think this all I can talk today. So thank you for your attention, and I'm happy to answer the questions.